I am Professor Shiva Panchakshari. In this video, I'm going to explain about the phase shift property of S matrix. This property can be stated in a simple way. It says that the phase of S parameters changes when the reference planes are shifted at the ports of microwave network or a device or junction. So if you look into the statement, you get an idea that S parameters phase changes. S parameters are basically complex. Sij is having both magnitude and phase. So when the reference planes are shifted, the phase of this S parameter, that is phi ig, changes. Magnitude does not change. So we shall look into the more aspects of this property. Generally, when you speak about the port of a microwave network, it is basically a transmission line or waveguide. So let us consider it as a transmission line for time being. The length of this transmission line used at the port, used as port, is small. And the energy applied at the port is of microwave frequency. You know that microwaves are gigahertz frequencies. Their wavelengths are very small. Wavelengths, that is lambda, are very small. So because of that, the voltage or current value on the transmission line that is used as port changes. So even though port length is small, the voltage will not remain constant. It changes, but the magnitude of the voltage or current on the entire port remains same because, as I said, the transmission lines are treated as lossless devices at microwave frequencies. So no dissipation takes place. Magnitude remains same, but the phase changes because of this smaller lambda. So if you make the measurement of voltage at this plane, let us say, then you can have this voltage value. If the plane is shifted, the plane of observation or the plane of measurement is shifted, then the voltage value changes. As I said, magnitude may remain same, but the phase changes. This change in phase is also very important in dealing with S parameters. So this property of the S matrix says that the phase of every S parameter changes when the reference planes are shifted, either outward or inward. So, and the amount of change in phase is proportional to this length, and the phase shift is given by the product of beta and L. Beta, as we all know, is the phase shift constant, is the phase shift constant or phase shift parameter, which is basically measured in radians per meter. So when beta is multiplied by the distance L, it gives the corresponding phase shift that would occur over this distance. So every shifting reference plane introduces an additional phase shift of phi to every voltage or current wave. This is what is the essence of this property. So when the reference planes are shifted in one port or more than one ports, the corresponding S parameters related to the port or ports are changed, but changed only in the phase, but not in the magnitude at microwave frequencies. So now let us discuss in detail about these changes by considering a two-port microwave network. So now let us consider a two-port microwave network of characteristic impedance Z0 which is designed for microwave applications. Right. So for this two-port network, let us define the reference planes as RP1 and RP2. RP1 and RP2 are the reference planes, are the planes of observations, are the planes of measurements for port 1 and port 2 respectively, at which the S matrix is defined. The S matrix is defined as S11 you know that for two-port network, the order of S matrix is 2. So 2 cross 2 matrix, 4 elements. So these are the S parameters defined for these two reference planes, RP1 and RP2. And these S parameters are defined in terms of the normalized voltage waves or current waves. So we know that A1 is the normalized incident wave that is produced by the excitation source. B1 is the normalized reflected wave produced by the network. So A1 is normalized incident voltage wave or current wave. V plus is the incident wave, and V plus when divided by root Z0. Root Z0 is a constant here for a given network. So A1 becomes the normalized incident wave. Similarly, V1 is the normalized reflected wave So accordingly, A1 and B1 are defined. Now similarly, for port 2 also, we have A and B values. So B is reflected by the network. Okay. So now, if the reference planes are changed, for example, if the reference planes are shifted outward to new positions like RP1 dash, RP2 dash, then the values of A and B are also changed. So now A is measured at this point as A1 dash. B is also measured at the same reference plane as B1 dash. Similarly, at port 2 also happen. So now look at this carefully. The diagrams will speak everything what's happening. Point 1 to be noted is the reference planes are shifted through a distance of L1 and L2 at the ports 1 and 2 respectively. This distances L1 and L2 gives us the phase shift of phi1 and phi2 respectively. So the phase shifts phi1 and phi2 are due to the change in the reference planes at the ports 1 and 2 through the distances L1 and L2 respectively. So if you look at carefully here, the relation between A1 and A1 dash, B1 and B1 dash, we'll get some interesting points. Here, A1 is the incident wave produced by the source, which is traveling through this distance by the time it reaches the reference plane, 1. But after shifting in the reference plane to RP1 dash, the distance traveled by the incident wave is only this much, which is less than the previous one. So time taken by A1 dash is less than the time taken by A1. So this change in time taken is represented as phase shift. So A1 dash is having a phase advance with respect to A1. When the time taken is less, that becomes a phase advance. When the time taken is more, so that is represented as phase delay. That is happening in the case of B1 here. See, for the first reference plane, the reflected wave has gone through this distance. For the second plane, it is traveling much more distance. So it takes more time to reach second plane. So the phase shift corresponds to phase delay. So the reflected voltage wave undergoes a phase delay of phi1 and incident wave undergoes a phase advance of phi1 at port 1. Similarly, the corresponding things are happening at port 2 also. So I can write now the equations for these new quantities. Therefore, now B1 dash becomes B1 into e power minus j phi 1. So the original B1 is added with an additional phase of phi 1. Minus sign indicates the phase delay. So more time taken would become B1 dash. Similarly, B2 dash can be represented in the same. Similarly, A1 dash can be written as A1 into e power j phi 1. It undergoes same phase shift of phi 1, but you can see positive sign there indicating phase advance, and A2 dash also phi 2, e power j phi 2. So all the B's are having negative phase and A is the positive phase. Accordingly, we can understand that they are phase delays and phase advances. So now we can define the new S parameters for the new reference planes, that is S11 dash as B1 dash by A1 dash. Assuming port 2 is perfectly matched. So when the port 2 is perfectly matched, we can define two S parameters, S11 and S21. So here the B1 dash is B1 e power minus j phi 1 and A1 dash is A1 e power plus j phi 1. So if you consider this ratio B1 by A1, that is S11, then other two terms give us e power minus j 2 phi 1. So in summary, the new S parameter, that is the reflection coefficient at port 1, S11 dash, is the new value which is obtained by multiplying S11 with e power minus j 2 phi 1. Minus indicates delay, 2 phi 1 indicates double the phase shift. One comes from A, another comes from B. Similarly, we can find quickly the other three S parameters also the same way. Let us go to S21 dash. This is given by B2 dash A1 dash, and B2 dash is B2 e power minus j phi 2. A1 dash is A1 e power plus j phi 1. So B2 by A1 is S21, the initial value, and the exponential terms give us phi 1 plus phi 2 within the bracket. So this is a new value here, second S parameter. So you can label them. So now we shall shift to other port now. Assuming that port 1 is matched, load is shifted to the side, we can define another S parameter. We know that it is S12 dash. So by definition, it is given by B1 dash by A2 dash, B1 e power minus j phi 1, A2 e power plus j phi 2. So this gives us phi 1 plus phi 2. So now we'll go for the fourth one, the last one. Reflection coefficient at port 2 is 2 dash. is by definition B2 dash by A2 dash. B2 dash is B2 e power minus j phi 2 A2 e power j plus phi 2. This is S22 multiplied by e power minus j 2 phi 2. So we have calculated all the four parameters. So we can combine them and write the new S matrix. Therefore, the new S matrix for the reference planes. So which are the reference planes defined for the reference planes? RP1 dash and RP2 dash is so the new S parameter or the new S matrix is denoted as S dash matrix having the elements S11 dash, S12 dash, S21 dash, S22 dash. So we'll introduce the derived equations into this new S matrix. So that becomes S11 e power minus j 2 phi 1. Here S21 is e power minus j phi 1 plus phi 2. S12 is e power minus j phi 1 plus phi 2, and S22 is e power minus j 2 times phi 2. So you can observe that the reflection coefficients are confined to specific port, so they're having only corresponding phase shifts. So S11 having only phi 1, S22 only phi 2. But S1 to S21 being transmission coefficient related to both port 1 and port 2, they're having are related to both the phase shifts phi 1 and phi 2. So this S matrix, new S matrix, can be mathematically decomposed into three different matrices. This way. The new S matrix X dash can now be written as e power minus j phi 1, 0, 0, j phi 2. This gives us an idea to write new S matrices easily. Okay. So if you perform multiplication of these three matrices, first these two, then the resultant with this. If you multiply them, then you will get the final S matrix what we got in the previous step. So let me conclude here with this. If you want to write the new S matrix for new set of reference planes shifted outward, then follow this method. First write here the phase shift at port 1, then here the phase shift at port 2. Then multiply this matrix with our old S matrix, which was defined for previous or earlier reference planes, then the resultant is again multiplied with this matrix. So this is the method of finding new S matrix through mathematics without conducting any experiments. So if we recall the statement of phase shift property, we can understand that the S parameters for new set of reference planes is always come with changed phases with respect to the original S matrix defined for old reference planes. So only phase shift changes, and the corresponding phase shifts can be calculated by this method. So that's it. Thank you.